Whatever you're using to watch this right now, your phone, your computer, your tablet.
It's all running because of a really simple but incredibly clever trick, a tiny adjustment made to a very common material.
And yeah, that material is silicon. But here's the kicker. It's not just plain old pure silicon. It's silicon that has been fundamentally transformed to make all of our modern tech possible.
So today, we're going to pull back the curtain and dive into the world of semiconductors. We're going to see how we take a pure, basic element and turn it into the literal brains of your smartphone.
Okay, so here's our roadmap. We'll start with the pure foundation. Then we'll look at the big problem with being pure. After that, we'll get into that clever trick called doping, check out the 2 flavors it creates, and finally, see the amazing payoff. All right, let's start at the very beginning, the material in its most basic, untouched state. That term, intrinsic semiconductor, sounds kind of technical, right? But honestly, it's just a fancy way of saying it's pure. Totally 100% pure. Think of it like a clean slate. We're talking about silicon or germanium with absolutely nothing extra mixed in.
So in a crystal of pure silicon, you've got all these atoms neatly linked up, sharing electrons to stay stable. But even at room temperature, a little bit of heat energy is enough to knock some of those electrons loose. And when an electron jumps out of its spot, it leaves behind, well, an empty space. We call that a hole. And this isn't just nothingness. It's like an open parking spot, an invitation for another electron to move in, which is crucial for carrying current.
And here's the most important part about this pure stuff. It's all about balance. For every single electron that breaks free and zips around, there is exactly one empty hole left behind. They're created as a pair, so their numbers are always equal.
So we have this perfectly balanced, pure material. Sounds great, doesn't it? Well, here's the thing. It's just not going to cut it if you want to build something like a computer chip.
And here's the big catch. That perfect balance means there are very few free electrons and holes running around, so it can't carry much of an electrical current. Pure silicon is actually a pretty bad conductor. It's not a complete wall like an insulator, but there is no way it's good enough to power the billions of things happening in your phone every single second.
So, scientists and engineers needed a fix, and what they came up with was just brilliant. So simple, but it completely changed the game.
That trick is called doping. It's kind of like being a chef for materials science. You take your pure silicon and you intentionally sprinkle in a tiny, super precise amount of something else, an impurity, and that tiny addition dramatically boosts its ability to conduct electricity. And once you've doped it, it's not intrinsic or pure anymore. Now it's called an extrinsic semiconductor. And this stuff, the doped version, is the real foundation of basically every electronic device we use today.
Now, here's where it gets really interesting. Doping isn't a one-size-fits-all kind of deal. Depending on what you sprinkle in, you can create 2 totally different but equally powerful types of material.
The choice of what to add all comes down to how many electrons that impurity has on its outer shell. On one hand, you've got pentavalent impurities like phosphorus. These have 5 outer electrons. That's 1 more than silicon is looking for. On the other hand, you have trivalent impurities like boron. They only have 3. That's 1 fewer than silicon needs.
So let's say you add a pentavalent impurity, like phosphorus. The phosphorus atom fits into the silicon grid. 4 of its electrons form bonds just fine, but that 5th one, it's just extra. It becomes a free electron, ready to move and carry current. This gives us what we call an N-type semiconductor, where the vast majority of charge carriers are these free electrons.
Okay, now let's go the other way. We add a trivalent impurity, like boron. The boron atom only has 3 electrons to share. When it tries to bond, it comes up 1 short, creating a deficit, an empty spot. Our hole is back. Think of that parking lot again. A car from a nearby spot can move in, leaving its old spot empty. The hole has effectively moved. This is a P-type semiconductor, where the main charge carriers are these mobile holes.
And you know what? There's a super simple way to remember all this. For N-type, just think N for negative, because electrons have a negative charge. For P-type, think P for positive, because a hole acts like a positive charge. Simple as that.
So let's put it all together real quick. We started with intrinsic silicon, pure, but with low conductivity. We used doping to create 2 new types, N-type, which is loaded with extra electrons from a pentavalent impurity, and P-type, which is full of holes thanks to a trivalent impurity. The bottom line?
Both doped versions have high conductivity, while the pure stuff has low conductivity. It's really that simple.
So we've gone from pure silicon to doped silicon with extra electrons and doped silicon with extra holes.
Why does any of this matter?
Well, this right here is where the magic really happens.
Because by strategically combining these N-type and P-type materials, layering them in just the right way, we can build everything. The transistor, that tiny little on-off switch that's the heart of all computing, that's made by layering them. Your phone's processor has billions of them. Diodes that act like one-way valves for electricity, the solar cells that power our world, they all work because of that special junction where N-type and P-type silicon meet.
It's honestly incredible to think about. This one simple trick of intentionally adding tiny imperfections to a pure material is the absolute bedrock of our entire digital age. It unlocked a level of control over electricity that has completely reshaped society. Which really makes you wonder, right? What other simple tricks are out there, just waiting to be discovered, that will enable the next great revolution?